Bismillah ar-Rahman ar-Rahim. This is Steel Structures class delivered by Dr. Qusay Al-Kaseasbeh from Mutah University. Today, inshallah, I'm going to continue with the staggered fasteners. And let's say if we do have angle shape, how we can get the gauge or how to visualize this and as a plate and get the gauge for this case. If you see here, so this leg, it has two lines of bolting, the bottom one with the 3 bolts and the second one here with 2 bolts. Okay, so, and this is the line, okay? This is the alignment of this line, and this is another line here. So if we unfold this leg, okay, make it half here, unfold it, put it here. So we do have a line of poles here with the 3 poles. So the G here, which is the distance from here to here, is equal to plus 3 minus the thickness, okay, minus the thickness, because if we take it 2 legs, because this distance from here to here, so there is 1/2, which is the thickness extra, 2 plus 3 minus the thickness, which is 1/2, this is 4.5 inch. So this is a G that we will use to find the net area. Let's solve example 3.7 on page 60, and I want to mention there are like many cases in, let's say, similar to this one with different cross sections. We will go through them later, okay? So right now let's solve example 3.7 and see how we use this node to solve an example and find the net area. Example 3.7 says an angle with staggered fasteners in each leg is shown in figure 3.17, and this is the figure 3.17. If you see here, we do have the cross section, 2 lines bolts. This is the first one here, and this is the second one here with 2 bolts. And if this is the, let's say, the cross section, so this is the side view here. If you look at this one from here, you will see these lines, and here is there are bolts, okay, 2 lines of bolts. If we unfolding this one, doing it, unfolding here, and we do, sorry for this, we do have 2 lines of bolts. This is the first one, this is the second one. So here we can get the G, and I'll show you how to get it, okay? These ones here are easy because they are here, and this one is here, but this one, which is this one, oh sorry, this one, it can't be get it directly, or it can't be cut directly, so we need to find that as we did in the angle shape in this class. Okay, let's get back and see what other information we do have. In this example, A36 steel is used, okay, and holes are for 7/8 inch diameter bolts. We need to determine the design strength for LRFD method, and we need to find the allowable strength for AST method. Let's say the steps for this example. First, we need to find the nominal strength based on yielding and the nominal strength based on fracture, based on LRFD method and AST method. But first, to find nominal yielding based on fracture, we need to find the net area and the effective net area. So the net area here, this is going to be the, let's say, the main interest in this question or this example. So if you see this one here, to find the net area, we might have more than one path. So this is going to be one path, which is A, B, D, F, and we're going to have another path with a different color here. Let's call it A, B, C, D, G. And we might have a third path, which I'll show you later in this example, okay? So how to solve this example with this or with this information? Okay, for the case, or let's say the path here, A, B, D, F, which is this one here, A, BDF. In this case, you know, we do have the net area is equal the gross area minus T times D, okay? Or let's say whole area, or area holes. Okay, from the manual, as I showed you in the last class, for L8 by 6 by 1/2, gross area is equal 6.8 inch square, and you can get it from there. So here, this one is gonna be 6.8 minus. How many bolts we do have in this path? We have 1 bolt, 2 bolts here. So there's gonna be 2, this is the number of bolts, times 1/2, this is the inch, times the diameter for the holes. 7/8 the diameter for the bolt, plus 1/8. So this is the diameter for the hole, and this is gonna be equal to 5.8 inch square. So this is the first path. What if we check the second path, which is A, B, C, E, G? Okay, so in this case, let me pick a different color here. The net area is going to be area gross, which is 6.8 minus. How many bolts we do have in this path? There is 1 here, 2, and 3, and we do have 1 inclined line. So this is going to be, let's say here in the first one, this is not inclined. This is very straight. So it's going to be the thickness 1/2 times the diameter for the holes, which is this one. It's 1 inch times 1 bolt. Okay. But if you notice, this one here is going to be similar to this one here. So we can do it directly and mention, okay, this is going to be, let's say, 2 bolts. يعني هون number of bolts اللي هم this one, okay? Minus. So we do have 1 bolt here, and this one is inclined. So it's gonna be 1/2 times 1 as the number of bolt. Okay, this is number of bolts, and the thickness here, or let's say the diameter, is 1 as the original diameter, اللي هو 7/8 plus 1/8. Okay, minus. How much here is the, let's say, S and G. S here, if you notice, 1/2. Okay, you can see it here. So this one is gonna be, let's say, I think this is 1. Okay, just a minute. It's this one, exactly this one. Okay, so it's gonna be 1/2. So 1/2 dividing by 4G, and the G here between this one and this one is 2.5 or 2.5. So if you do that, you will get the net area is 5.413 inch square. So right now we checked 2 paths. Let's right now check the path A, B, C, D, E, and G. Okay, so in this path, you know, the net area is equal the gross area, which is 6.8 for this cross section from the manual, minus the first one here is 3, so it's going to be 1/2. Okay, let's say times 1 bolt. This is number of bolts. Okay, of bolts, times how much the diameter for the hole here. It's going to be 7/8 plus 1/8, which is 1 inch. So it's going to be 1 inch. And then we have inclined here. So minus 1/2, 1 diameter, or let's say 1 bolt, times here inclined. So this is going to be 1, which is the original diameter, minus s square, and s here, if you see, it's 1/2 or 1.5, sorry, dividing by 4g, and g here is 2.5. Okay, this is square, forget, okay. Minus, so we do have another inclined line here. So it's 1/2 times 1 number of poles times 1 the original diameter or hole diameter minus what is the s here, it's same to this, so it's going to be 1.5 square 4 times g. And how much g in this case? If you see this guys, so this is 3 plus 2.25 minus the thickness, so this will be 4.75. So once again here, it's going to be g here, it's 3 plus 2.25 minus the thickness, which is 1/2. So this is going to be 4.75 inch, which is here. Okay, and we still have one inclined line here minus, so 1/2, which is the thickness, times 1 number of bolts, times 1 the original hole diameter minus 1.5, it's the s square dividing by 4 g, and g here is 3 meter, okay, sorry, 3 inch, and this one equals to this much, which is 5.06 inch or 5.065 inch square. So this path, it seems that the least or the smallest one, since we do have another 2 paths. The first one got us, let's say, 5.8, the second one 5.413, and the last one is 5.06, and this is the latest one, so we're gonna go with this one and assign this as a net area. So the net area is gonna be this much, okay? Here, let's assume U is equal 1, okay? So the effective net area is equal net area times U, which is 1, so it's going to be the same. The nominal strength here, based on, let's say, yielding first, it's going to be Fy times Ag. Fy is 36 and Ag is, or gross area, 6.8, so it's going to be 244.8 kips. For piston fracture, it's going to be Fu times effective net area, which is this one, it's going to be 58 times 5.065, and it's going to be this much, okay? So this is the nominal strength based on fracture, nominal strength based on yielding. So right now we can use either, let's say, LRFT method or AST method. For LRFT method, here, so the design strength based on yielding is going to be 0.9 times the nominal strength based on yielding, so it's going to be 220 kips. Based on a fracture, it's going to be 0.7 times the nominal strength based on fracture, so this is going to be 220 kips. So the design strength is going to be same for both, so it's not a matter which one you can, like, let's say, pick. So, but finally we can say that the design strength based on LRFT method is 220 kips. For AST method, for, let's say, yielding, this one is going to be the nominal strength. So for yielding, it's going to be, let's say, here I'm dividing the safety factor. So the nominal strength based on yielding is, let's say, 244.8 dividing 1.6. And for fracture, this one, it's going to be Pn dividing by safety factor, which is 2. So this is going to be 293.8 dividing by 2. And this one, it will get us, let's say here, the values for the allowable strength. And so this one is going to be 146.9 kip, and the other one is going to be this much. It's almost same, but this is the least, so we're gonna get the one based on the yielding as a control. So and this example showed us how to find the net area for staggered paths and how to pick the smallest one, and then we can continue as usual with the procedure we have been taught earlier. In example 3.8, we let's say determine the smallest net area for American Standard Channel, which is shown in the figure 3.18. The holes for this let's say 3.18. So I'm gonna leave this question for you so you can solve it. It's not that let's say complicated question. There are here some let's say cases we need to talk about and see how we're gonna get the gauge for these cross sections. So in this example, if we do have, let's see, C channel, the C channel we had in example 3.8 is, let's say, has no line of bolts in the, let's say here, the flange, but this one it has. So what we can do, just like do it this way. So this is line of bolts, this is the second line of bolts. So if we fold this in this way and fold it in this way, we do have one line here, which is the one here. We do have another line here, which is the one here. So the gauge here, it's going to be G1 plus G minus the thickness of the web. Okay, so this one, I think it's easy and it's not that hard. This is, if you look side, let's say here, front of you, you will see this one here. That's what we do have here, and this one is very important, guys. Since we do have, let's say here, S shape. This is S shape. It has two lines of bolts here in the web. Okay, and we do have two in each flange. Okay, so if you look from, let's say, front, you will see this one here. Okay, so how to unfold this and get the gauge for this one. So this one, as imagine you are taking it from here, or let's imagine it this way, that you are taking it at the mid here. Okay, imagine this is at the mid. Okay, so this one here is half of the web thickness. Okay, so in this case, if we, let's say, let me do it here, guys. I think that much easier for all. So we do have one line of bolt here, another line of bolt here, and let's say this is G. So if we take, let me pick a different color here. If we take it from the middle here, okay, so this one here, this distance, let's say this one is web thickness over 2, and fold this or unfold it, sorry, here it's gonna be like this, but you know this distance, which is it's gonna be extra. Okay, so this one is gonna be G1 plus G2 over 2, sorry, G over 2, which is this one, minus the half of the web thickness. Okay, so that's what we get for this one. Once again, two lines of bolts. Right now, take the half of this one and unfold it to become like this. Okay. But you know, Hone, this distance is going to be extra here, so we have to take it out. This is what we refer to here, minus the thickness of the web over 2, and here is the G, so the distance here was G over 2. Okay, so I think this is easy right now, so you can use it. Let's solve example 3.9. So in this example, we need to find the available strength of the S shape shown in figure 3.20. I'll show you the figure soon. The holes are for 3/4 inch diameter bolts, and we need to use A36 steel. So here, So this is the shape, which is S shape 15 by 50. And if we unfold this one, let me show you how to do that again here. So take it from the middle here, okay, and take it up this way. So we do have two lines of folding here. They are, let's say, identical to each other. So we do have two lines here. Same here. So this one so here we need to get the G. So the G here is equal this distance, which is G1 to 75 plus G dividing by 2, which is 3.5 dividing by 2 minus the thickness of the web, and we will get that half of the thickness of the web. We will get that from the manual. Okay, so here we do have, let's say, more than one path. We might go with path AD, okay, or we might go with path, let's say, A, B, C, and D. And let me show you how to do that. But first, let's go to the manual and get the information we need for this section. So here we need the web thickness, and we need the flange, this is the flange thickness, and we need the web thickness, and we need the gross area. Okay, hold a second. Okay, if you go to the, let's say, table 1.3 in the steel manual, part 1, and look for S shape 15 by 50, so this is the area, you see the area in the inch, and here is the web and flange thickness. So the web thickness is 0.55, and the flange thickness is 0.622. Okay, so these all the information we need to continue with our example 3.9. So for the line, let's say AD, we do have, let's say, gross area 14.7 minus here. This is very important point. So when we talk about AD, here we do have two lines of bolts. So we have two lines here, and we do have two lines here. Okay, so that is for here. And 7/8, because we do have 3/4 for the bolts, 1/8 for, let's say, the hole. So the hole diameter is 7/8 times, where is these are in the flange. So we do have the flange thickness here from the manual point, 622, yeah, and the net area for this path is equal 12.52. Okay, so what if we're gonna check the path A, B, C, D? Okay, in this one here, we're gonna, let's say, do it here. So area or net area is equal, let's say here, 2 bolts. This is number of bolts. Okay, times the thickness of the flange, which is this much. Okay, times the hole diameter. Okay, so this is the first one, minus, and here we have inclination or inclined line. So this is one. This one is going to be 1 bolt times the thickness of the web is 0.55 from the manual times the 7/8, which is the just a minute here, 7/8, yeah, minus because we have inclination here, so S here is 1.5, and G, as we calculated, is this much. So this one is going to be 1.5 square dividing by 4 times G, and G is this much as we did calculated here. Okay, and we still have bolt here, and this bolt is minus 1 bolt times the thickness of the web, and thickness depends where you are. Okay, times 7/8, which is the diameter for the hole. This is straight, we don't need to do this part. Minus here, we have 2 poles here, so 2 times the thickness of the flange, which is this much, times 7/8 minus S is 1.5, again dividing by 4 times this one here, G, okay, here, it's going to be same here because it's asymmetrical. So it's going to be 4.22, and this one here is going to be the net area for the path A, B, C, D, and which we'll see here. Let me show you the result for this one and this one here. Yeah, this is the value. If you notice, that was 12 point something, this is 11, so this is the control. So since this is the control, let's say all the elements of the cross section are connected, but all the time I'll tell you that U, or the shear lag coefficient, is equal 1. So the effective net area is equal to the net area. So right now we can get the nominal strength based on, let's say, fracture, and based on yielding. Based on yielding, it's going to be 36 times the cross area from the manual. So it's going to be 529.2. For the fracture, it's going to be the ultimate strength, which is, or stress is 58 KSI times the effective net area, the one we just calculated. So here, so right now, once we got the nominal strength for, let's say, based on yielding, based on the fracture, we can use either LRFD method or ASD method to get the design strength and the allowable strength respectively. So for LRFD method, here we just can say that based on the fracture, this is going to be 0.5 times the nominal strength based on the fracture. Based on yielding, 0.9 times the, let's say, nominal strength based on yielding. So we can get this much, which is 510 kip for fracture and 476 for yielding. So the yielding will be the smallest and the control. Okay. If we do that for ASD method, so we can do that. I like to do it this way. For yielding, I'm talking about the ASD method. For yielding, it's going to be, let's say, Pn dividing by the safety factor. For yielding, this one is for yielding. So it's 529.2 dividing 1.67. And for fracture, this one is Pn dividing by, so this one is equal this much, 680.3 dividing by 2. Solving this, you will get this one here, kip, and this one here, it's gonna be, let me come up with the correct answer for this one. So it's gonna be 315.9 kip. So this one is the smallest. So yielding is going to be control in both cases, LRFD method and ASD method. I'm going to stop here today, guys. So please, if you do have any questions, you can send me an email or chat with me on Microsoft Teams. Thank you.